What if the universe had secret shortcuts, hidden tunnels that could whisk you across galaxies in the time it takes to blink? This isn't science fiction. It's the tantalizing promise of wormholes and faster-than-light travel, two of the most mind-bending ideas in modern physics. These concepts don't just challenge our understanding of space and time, they shatter it, offering glimpses of a reality where the impossible becomes possible. From bending the fabric of spacetime to outrunning light itself, the theories we're about to explore will take you on a journey through the cosmos that defies everything you thought you knew. Over the next few minutes, we'll dive into 25 incredible ideas that could revolutionize how we see the universe and our place within it. Get ready to question the very nature of reality as we uncover the secrets of wormholes, faster-than-light travel, and the extraordinary possibilities they hold. Let's start at the very beginning, where the idea of wormholes first took root in the scientific imagination. Back in the 1930s, Albert Einstein and his colleague Nathan Rosen were exploring the implications of general relativity, Einstein's revolutionary theory of gravity. What they discovered was nothing short of astonishing. Hidden within the equations of general relativity were solutions that suggested the existence of bridges through spacetime. These bridges, now famously known as Einstein-Rosen Bridges, were essentially shortcuts, hypothetical tunnels that could connect two distant points in the universe, potentially allowing travel across vast cosmic distances in an instant. At their core, these bridges are a natural consequence of the way spacetime bends and warps under the influence of gravity. Imagine spacetime as a vast, stretchy sheet. If you place a heavy object on it, like a star or a black hole, the sheet dips and curves. Now, picture two such dips far apart on the sheet. An Einstein-Rosen bridge would be like a tunnel connecting those two dips, creating a direct path between them. Mathematically, this makes perfect sense, but here's the catch. These bridges, as Einstein and Rosen described them, are incredibly unstable. They're more like cosmic mirages than practical shortcuts, appearing in the math but vanishing before anything could actually pass through. This instability is just one of the many challenges that make wormholes so fascinating and so elusive. While Einstein and Rosen's work laid the foundation for modern wormhole theories, it also opened up a Pandora's box of questions. Could these bridges ever be stabilized? What would it take to make them traversable? And if they could exist, what would that mean for our understanding of the universe? These are the mysteries that physicists have been grappling with ever since, and they're the questions that will guide us as we explore the next steps in the evolution of wormhole theory. So, if Einstein-Rosen bridges are so unstable, how could we ever hope to use them for interstellar travel? Enter the idea of traversable wormholes, a concept that takes the original Einstein-Rosen bridge and asks, what if we could make it work? This is where physicists like Kip Thorne stepped in, pushing the boundaries of what we thought was possible. Thorne, a Nobel Prize-winning physicist, took the theoretical framework of wormholes and asked a daring question: could we stabilize them? The answer, it turns out, lies in something called exotic matter. Exotic matter isn't your everyday material. It's a hypothetical substance with properties that defy the laws of physics as we know them. Specifically, it would need to have negative energy. Negative energy is a strange concept, but think of it like this. While normal matter creates gravity that pulls things together, negative energy would do the opposite, pushing spacetime apart. This repulsive force could, in theory, counteract the natural tendency of a wormhole to collapse, keeping it open long enough for something or someone to pass through. But here's the catch: we've never actually observed exotic matter or negative energy in the universe. It exists only in the realm of theory, and creating or finding it would require technologies far beyond our current capabilities. Still, the idea is tantalizing. If we could somehow harness exotic matter, we might be able to create stable wormholes, turning them into cosmic highways that could connect distant stars, galaxies, or even universes. Imagine stepping through a portal and emerging light years away in the blink of an eye. The implications for humanity's future would be staggering, colonizing distant worlds, exploring alien civilizations, or even escaping a dying Earth. Of course, the challenges are immense. Beyond the need for exotic matter, traversable wormholes would require an enormous amount of energy, precise engineering, and a deep understanding of space-time that we simply don't have yet. But the dream persists, fueled by the possibility that one day we might crack the code and unlock the secrets of these cosmic shortcuts. And while wormholes offer one path to interstellar travel, they're not the only option. What if we could bypass the need for tunnels altogether and simply travel faster than light? This brings us to another mind-bending concept: faster-than-light travel, or FTL. Unlike wormholes, which bend spacetime to create shortcuts, FTL travel would involve moving through space at speeds that exceed the cosmic speed limit, the speed of light. But how could that even be possible? Let's dive into that next. The idea of traveling faster than light has long been a staple of science fiction, but could it ever become science fact? Faster-than-light travel, or FTL, is the concept of moving through space at speeds that exceed the speed of light, approximately 300,000 kilometers per second. According to Einstein's theory of relativity, this is the ultimate speed limit of the universe. Nothing with mass can reach or surpass it, and as you approach the speed of light, the energy required to go faster becomes infinite. This makes FTL travel seem impossible, at least within the framework of our current understanding of physics. But here's where things get interesting. While Einstein's laws appear to slam the door on FTL travel, they also leave a few cracks open, opportunities for creative thinking and theoretical workarounds. For instance, relativity doesn't forbid the universe itself from expanding faster than light. In fact, during the early moments of the Big Bang, the universe expanded at speeds far beyond the speed of light. This raises an intriguing question. If the fabric of spacetime can stretch faster than light, could we somehow harness that same principle for travel? One of the most promising ideas in this realm is the concept of warp drives. Popularized by science fiction, warp drives don't involve moving through space at faster than light speeds. Instead, they work by bending spacetime itself. Imagine a ship sitting inside a bubble of warped spacetime. The bubble contracts space in front of the ship and expands it behind, effectively allowing the ship to ride the wave of spacetime without actually breaking the speed limit. This idea, first proposed by physicist Miguel Alcubierre in the 1990s, is often referred to as the Alcubierre Drive. The Alcubierre Drive is a fascinating concept, but it comes with its own set of challenges. For one, it would require an enormous amount of energy, potentially equivalent to the mass energy of an entire planet. It would also need exotic matter with negative energy, much like the kind required for traversable wormholes. And even if we could overcome these hurdles, there's the question of whether such a drive would be safe or practical. Could a ship survive the intense gravitational forces inside a warp bubble? What would happen to the regions of space it passes through? Despite these obstacles, the Alcubierre Drive remains a tantalizing possibility, and physicists continue to explore ways to make it more feasible. Some have proposed modifications to the original concept, suggesting that less energy or different types of exotic matter might be sufficient. Others have even speculated that quantum mechanics or advanced technologies we haven't yet discovered could one day make warp drives a reality. But warp drives aren't the only theoretical path to FTL travel. Another intriguing idea involves tachyons, hypothetical particles that, if they exist, would always travel faster than light. Unlike normal particles, tachyons would have imaginary mass, a concept that's as strange as it sounds. While tachyons remain purely theoretical, they've captured the imagination of scientists and science fiction writers alike, offering a glimpse of a universe where the speed of light isn't the final frontier. The pursuit of FTL travel isn't just about breaking records or reaching distant stars. It's about pushing the boundaries of human knowledge and exploring the fundamental nature of reality. Whether through warp drives, tachyons, or some yet-to-be-discovered phenomenon, the dream of faster-than-light travel continues to inspire us to think beyond the limits of what we know. And as we'll see next, some of the most innovative theories in physics are already pointing the way toward possibilities we once thought were pure fantasy. What if the key to faster-than-light travel isn't about moving faster, but about bending the rules of space itself? This is the core idea behind the Alcubierre Drive, a theoretical model proposed by physicist Miguel Alcubierre in the 1990s. Unlike traditional propulsion systems that push a spacecraft through space, the Alcubierre Drive takes a radically different approach. It warps spacetime around the ship, creating a warp bubble that allows the vessel to travel vast distances without actually moving through space at all. Here's how it works. Imagine spacetime as a flat sheet of paper. Normally, to get from one point to another, you'd have to travel across the surface of the sheet. But what if you could fold the paper, bringing those 2 points closer together? The Alcubierre Drive does something similar. It contracts spacetime in front of the ship and expands it behind, effectively creating a shortcut. The ship itself remains stationary within the bubble, while the bubble moves through spacetime at speeds that could, in theory, exceed the speed of light. But there's a catch. To create this warp bubble, you'd need something called exotic matter, a hypothetical substance with negative energy. Exotic matter isn't like anything we've ever encountered. It would have to produce a repulsive gravitational effect, pushing spacetime apart rather than pulling it together. This is the opposite of how normal matter behaves, and it's essential for stabilizing the warp bubble and preventing it from collapsing. The problem: exotic matter has never been observed in nature, and creating it would require technologies far beyond our current capabilities. Even if we could produce it, the energy requirements for an Alcubierre Drive are staggering. Some estimates suggest it would take the equivalent of the mass energy of an entire planet just to power a single trip. And that's not even considering the potential dangers. What happens to the regions of space that are warped? Could the drive create destructive gravitational waves or leave behind hazardous distortions in spacetime? Despite these challenges, the Alcubierre Drive remains one of the most compelling ideas in the quest for faster-than-light travel. It's a testament to human ingenuity, showing how we can use the laws of physics not to break the rules but to bend them in creative ways. And while the drive may still be far from reality, it has inspired a wave of research into alternative approaches to FTL travel. One such approach involves wormholes, which we've already explored, but there are others that push the boundaries even further. For example, some physicists have proposed using quantum entanglement, a phenomenon where particles become linked across vast distances, to transmit information faster than light. Others have speculated about cosmic strings, hypothetical one-dimensional defects in spacetime that could act as natural highways for FTL travel. Each of these ideas offers a unique perspective on how we might one day traverse the cosmos, and together, they paint a picture of a future where the stars are no longer out of reach. The Alcubierre Drive is just one piece of the puzzle, but it's a reminder that the universe is full of possibilities waiting to be discovered. And as we continue to explore these theories, we're not just dreaming of distant stars, we're redefining what it means to explore the cosmos. Now, let's turn our attention to another fascinating concept: the idea of tachyons, hypothetical particles that might already be traveling faster than light. Could they hold the key to unlocking the secrets of FTL travel? Let's find out. What if wormholes could do more than just connect distant points in space? What if they could also bend time itself, offering a gateway to the past or the future? This is the mind-bending possibility that some physicists have explored, suggesting that wormholes might not just be cosmic shortcuts, they could also function as time machines. The idea hinges on a concept called closed time-like curves, or CTC. These are paths through spacetime that loop back on themselves, creating a kind of cosmic circuit. If you could follow one of these curves, you might end up right back where you started, but at an earlier point in time. Wormholes, with their ability to warp spacetime, could theoretically create such curves, allowing for time travel. Here's how it might work. Imagine a wormhole with one end stationary and the other end moving at near light speed. According to Einstein's theory of relativity, time slows down for objects moving at high speeds, a phenomenon known as time dilation. This means that while only a few minutes might pass for the moving end of the wormhole, years or even centuries could pass for the stationary end. If you were to step into the moving end, you could emerge from the stationary end in the past, effectively traveling backward in time. But before you start planning your trip to the age of dinosaurs, there's a catch. Time travel through wormholes comes with a host of paradoxes, the most famous of which is the grandfather paradox. Imagine traveling back in time and accidentally preventing your own birth. How could you exist to make the trip in the first place? This paradox highlights the logical inconsistencies that arise when time travel is introduced, and it's one of the reasons why many physicists remain skeptical about the possibility of CTCs. Still, the theoretical basis for wormholes as time machines is fascinating, and it raises profound questions about the nature of time itself. Is time a fixed, unchangeable dimension, or is it more fluid, capable of bending and looping? And if time travel were possible, what would that mean for our understanding of cause and effect? Beyond the physics, there are also ethical and philosophical implications to consider. If we could travel through time, how would we use that power? Would we intervene in historical events or simply observe? Could we prevent tragedies, or would our actions create even greater chaos? These questions don't have easy answers, but they remind us that the pursuit of knowledge often comes with profound responsibilities. While the idea of wormholes as time machines remains speculative, it's a testament to the creativity and ambition of human thought. It challenges us to think beyond the limits of our current understanding and imagine a universe where the boundaries of space and time are not as rigid as they seem. And as we continue to explore these possibilities, we're not just dreaming of distant stars, we're redefining what it means to explore the very fabric of reality. Now let's shift our focus to another intriguing question. What if wormholes aren't just theoretical constructs, but actual features of the universe? Could they exist naturally, hidden in the depths of space, waiting to be discovered? Let's explore that next. What if the strange behavior of particles at the quantum level could reveal secrets about the structure of spacetime itself? This is the fascinating idea behind the EPR conjecture, a theory that suggests a deep connection between quantum entanglement and wormholes. Quantum entanglement is one of the most puzzling phenomena in physics, where two particles become linked in such a way that the state of one instantly influences the other, no matter how far apart they are. This spooky action at a distance, as Einstein famously called it, seems to defy our everyday understanding of space and time. But what if this entanglement isn't just a quirk of quantum mechanics? What if it's a clue to something much bigger? The EPR conjecture, proposed by physicists Juan Maldacena and Leonard Susskind, suggests that entangled particles might be connected by microscopic wormholes. In this view, the entanglement isn't just a mathematical relationship, it's a physical bridge through space-time. Imagine two particles separated by vast distances, yet linked by an invisible tunnel that allows information to flow between them instantaneously. This idea blurs the line between quantum mechanics and general relativity, two of the most successful but seemingly incompatible theories in physics. If the EPR conjecture is correct, it could revolutionize our understanding of the universe. It would mean that the fabric of space-time is woven together by countless tiny wormholes, connecting particles in a vast, intricate network. This could help explain some of the deepest mysteries of quantum mechanics, such as how information is preserved in black holes, a problem that has puzzled physicists for decades. It also raises the tantalizing possibility that wormholes might not just be cosmic shortcuts, but fundamental building blocks of reality itself. But how does this connect to black holes, those enigmatic objects that warp spacetime to its limits? Black holes play a crucial role in wormhole theory, and they might hold the key to understanding the ER=EPR conjecture. According to some theories, the intense gravitational fields of black holes could create the conditions necessary for wormholes to form. In fact, the original Einstein-Rosen Bridges were proposed as a way to describe the extreme curvature of spacetime near a black hole. This brings us to an even more intriguing possibility. Could black holes themselves be gateways to wormholes? Some physicists have speculated that the singularity at the center of a black hole, a point of infinite density, might not be the end of the road. Instead, it could be the entrance to a wormhole, leading to another part of the universe or even another universe entirely. While this idea remains speculative, it highlights the profound connections between black holes, wormholes, and the quantum realm. The ER=EPR conjecture is still in its early stages, and much work remains to be done to test its validity. But it's a powerful reminder of how interconnected the universe might be, from the smallest particles to the largest cosmic structures. By exploring these connections, we're not just uncovering the secrets of wormholes, we're piecing together the very fabric of reality. Now, let's turn our attention to another cosmic mystery: the role of black holes in wormhole theory. Could these gravitational giants be the key to unlocking the secrets of spacetime itself? Let's dive deeper into that next. Black holes have long been some of the most mysterious objects in the universe, devouring everything that comes too close and warping spacetime to its limits. But what if these cosmic giants aren't just destructive forces? What if they're also gateways, portals to other parts of the universe, or even to entirely different universes? This is where the connection between black holes and wormholes comes into play, offering a tantalizing glimpse into the possibilities hidden within the fabric of spacetime. At the heart of this idea is the concept that black holes might not be dead ends. Instead, they could be entrances to wormholes, tunnels that connect distant regions of space or even bridge entirely separate universes. This theory builds on the original Einstein-Rosen Bridges, which suggested that the extreme curvature of spacetime near a black hole could create a passageway to another location. But here's the twist: if a black hole is one end of the wormhole, what's on the other side? Enter the concept of white holes. While black holes are known for pulling everything in, white holes are their theoretical opposites, regions of spacetime that expel matter and energy instead of absorbing them. Imagine a black hole as a one-way door and a white hole as the exit. If a wormhole connects a black hole to a white hole, it could create a cosmic tunnel where matter enters through the black hole and emerges from the white hole, potentially in a completely different part of the universe, or even in a different universe altogether. This idea of wormholes as bridges between universes is both thrilling and speculative. It raises questions about the nature of reality itself. Could our universe be just one of many, connected by a vast network of wormholes? And if so, what would these other universes be like? Would they follow the same physical laws, or could they be entirely different, with alternate dimensions or even different constants of nature? Of course, the challenges are immense. For one, white holes have never been observed, and their existence remains purely theoretical. Even if they do exist, the journey through a black hole wormhole, white hole system would be fraught with danger. The intense gravitational forces near a black hole would stretch and compress anything passing through in a process known as spaghettification. And even if you survived that, there's no guarantee the wormhole would be stable or that the white hole would lead somewhere hospitable. But let's set aside the practical challenges for a moment and focus on the bigger picture. The idea of black holes as gateways to other universes challenges our understanding of the cosmos and pushes the boundaries of what we thought was possible. It suggests that the universe might be far more interconnected than we ever imagined, with hidden pathways waiting to be discovered. This brings us back to the concept of wormholes as cosmic shortcuts. If black holes and wormholes are indeed connected, they could offer a way to traverse vast distances in the blink of an eye. Imagine a future where humanity has mastered the technology to navigate these cosmic tunnels, allowing us to explore distant galaxies or even other universes. The implications for science, philosophy, and our place in the cosmos would be profound. As we continue to explore these ideas, we're not just dreaming of distant stars, we're redefining what it means to explore the universe itself. The connection between black holes and wormholes is a reminder that the cosmos is full of mysteries waiting to be uncovered, and that the answers might lie in the most unexpected places. Now, let's shift our focus to another intriguing possibility. What if wormholes aren't just cosmic shortcuts but also time machines? Could they allow us to travel not just through space but through time as well? Let's explore that next. What if the universe itself provided the tools to build wormholes? Enter cosmic strings, hypothetical one-dimensional structures that could hold the key to creating stable pathways through spacetime. These cosmic strings are thought to be remnants from the early universe, formed during the intense energy fluctuations that followed the Big Bang. Unlike anything we've ever observed, they're incredibly thin but possess immense density, stretching across vast cosmic distances like invisible threads woven into the fabric of reality. The idea of using cosmic strings to construct wormholes is as fascinating as it is complex. Imagine these strings as cosmic ropes that can bend and twist spacetime around them. If two cosmic strings were to move in parallel at incredibly high speeds, they could theoretically create a region of spacetime so warped that it forms a wormhole. This wormhole wouldn't just be a fleeting mathematical curiosity, it could be stable enough to serve as a practical shortcut through the universe. But here's the catch: cosmic strings, if they exist, are incredibly elusive. They're so thin and faint that detecting them would require technology far beyond what we currently have. Some theories suggest that cosmic strings might leave behind faint gravitational waves or distortions in the cosmic microwave background, clues that could one day help us find them. Until then, they remain a tantalizing possibility, a reminder of how much we still have to learn about the universe. Even if we could locate cosmic strings, harnessing them to build wormholes would be a monumental challenge. The energy required to manipulate these structures would be staggering, and the precision needed to create a stable wormhole would push the boundaries of our engineering capabilities. But the potential rewards are equally staggering. A wormhole constructed with cosmic strings could offer a reliable, long-lasting pathway between distant points in the universe, opening up possibilities for exploration and travel that we can barely imagine. This brings us to another intriguing question. What role does dark energy play in all of this? Dark energy, the mysterious force driving the accelerated expansion of the universe, might hold the key to stabilizing wormholes. Some theories suggest that dark energy's repulsive effect could counteract the natural tendency of wormholes to collapse, acting as a kind of cosmic glue to keep them open. If true, this would mean that the same force pushing galaxies apart could also help us build bridges between them. The interplay between cosmic strings, dark energy, and wormholes is a reminder of how interconnected the universe might be. It's a puzzle with pieces that span from the smallest quantum scales to the largest cosmic structures, and solving it could unlock some of the deepest mysteries of existence. While the challenges are immense, the possibilities are equally profound, offering a glimpse of a future where the stars are no longer out of reach. As we continue to explore these ideas, we're not just dreaming of distant galaxies, we're redefining what it means to explore the very fabric of reality. And with each new discovery, we move one step closer to understanding the universe's hidden pathways and the extraordinary potential they hold. Now, let's turn our attention to another cosmic mystery, the role of quantum mechanics in wormhole theory. Could the strange behavior of particles at the smallest scales reveal secrets about the structure of spacetime itself? Let's dive deeper into that next. What if the very force that's tearing the universe apart could also hold the key to keeping wormholes open? This is where dark energy, one of the most enigmatic forces in the cosmos, comes into play. Dark energy is the mysterious force driving the accelerated expansion of the universe, pushing galaxies apart faster and faster over time. But its role might not be limited to shaping the large-scale structure of the cosmos. Some physicists believe it could also play a crucial role in stabilizing wormholes, acting as a kind of cosmic glue to keep these spacetime tunnels from collapsing. To understand how this might work, let's revisit the challenges of wormhole stability. As we've seen, wormholes are incredibly fragile structures. Without some form of exotic matter or negative energy to counteract the immense gravitational forces at play, they would collapse almost instantly. But what if dark energy, with its repulsive effect on spacetime, could provide the necessary counterbalance? Imagine dark energy as a kind of cosmic pressure, pushing outward against the inward pull of gravity. In theory, this outward pressure could keep a wormhole open, preventing it from snapping shut like a rubber band stretched too far. This idea is still speculative, but it's grounded in the strange and counterintuitive nature of dark energy itself. Unlike gravity, which pulls matter together, dark energy pushes it apart. This repulsive force is what's causing the universe to expand at an accelerating rate, and it's possible that the same force could be harnessed to stabilize wormholes. If true, it would mean that the very thing driving galaxies apart could also help us build bridges between them. But dark energy isn't just a potential tool for wormhole engineering. It might also hold clues to the nature of spacetime itself. Some theories suggest that dark energy could be linked to the vacuum energy of empty space, a kind of background energy that permeates the universe. If this is the case, then manipulating dark energy could give us unprecedented control over the fabric of spacetime, opening up possibilities for wormholes, faster than light travel, and even more exotic phenomena. This brings us to an even more mind-bending possibility. Could wormholes stabilized by dark energy serve as portals to parallel universes? The idea of parallel universes, other realms of existence with their own physical laws and histories, has long fascinated scientists and science fiction writers alike. If wormholes could connect not just distant points in our universe but entirely separate universes, the implications would be staggering. Imagine stepping through a wormhole and emerging in a reality where the laws of physics are subtly different, or where history took a completely different turn. Of course, this is still firmly in the realm of theory, and the challenges are immense. We don't yet fully understand dark energy, let alone how to manipulate it. And the idea of parallel universes remains one of the most speculative areas of modern physics. But the connection between dark energy, wormholes, and parallel universes is a reminder of how interconnected the cosmos might be. It suggests that the universe is far more complex and far more wondrous than we ever imagined. As we continue to explore these ideas, we're not just uncovering the secrets of wormholes, we're peering into the very heart of reality itself. And with each new discovery, we move one step closer to understanding the universe's hidden pathways and the extraordinary potential they hold. Now, let's turn our attention to another cosmic mystery: the role of quantum mechanics in wormhole theory. Could the strange behavior of particles at the smallest scales reveal secrets about the structure of spacetime itself? Let's dive deeper into that next. What if wormholes aren't just shortcuts through our universe, but gateways to entirely different realities? This is the mind-bending idea that some physicists have proposed. Wormholes could connect our universe to parallel universes within the multiverse. The multiverse theory suggests that our universe might be just one of countless others, each with its own unique set of physical laws, constants, and histories. If wormholes could bridge these universes, they wouldn't just revolutionize space travel, they'd redefine our understanding of existence itself. the concept of parallel universes isn't just science fiction. It's rooted in serious scientific theories such as string theory and quantum mechanics. String theory, for example, suggests that our universe might be one of many brains, short for membranes, floating in a higher dimensional space. These brains could be separated by vast distances, but wormholes might provide a way to traverse between them. Imagine stepping through a wormhole and emerging in a universe where gravity is stronger, time flows backward, or even where you might encounter alternate versions of yourself. But how could wormholes connect to these parallel universes? One possibility lies in the extreme curvature of spacetime near a wormhole's entrance. If a wormhole's throat, the tunnel connecting its two ends, extends far enough, it might not just bridge 2 points in our universe, but could instead link to an entirely different brain or universe. This idea is speculative, but it's supported by some interpretations of quantum mechanics and general relativity, which suggest that spacetime might be far more flexible and interconnected than we realize. The implications of this theory are staggering. If wormholes could connect to parallel universes, they might offer a way to test the multiverse hypothesis, one of the most profound questions in cosmology. For example, if we could detect a wormhole and observe particles or energy emerging from it, we might find evidence of another universe's physical laws. This could provide the first concrete proof that our universe is just one of many, fundamentally changing how we see reality. However, the idea of traversing wormholes to reach parallel universes comes with significant risks. The journey through a wormhole could be incredibly hazardous, with extreme gravitational forces, radiation, and the potential for instability. Even if a wormhole were stable enough to traverse, there's no guarantee that the destination would be safe or hospitable. You might emerge in a universe with incompatible physical laws, where matter as we know it couldn't exist, or where time itself behaves unpredictably. And then there's the question of what or who might be on the other side. If wormholes connect to parallel universes, could they also serve as pathways for other civilizations to reach us? The idea of encountering intelligent life from another universe is both thrilling and terrifying, raising questions about how we'd communicate, coexist, or even defend ourselves. Despite these challenges, the idea of wormholes as multiverse gateways continues to captivate scientists and dreamers alike. It's a reminder that the universe, or multiverse, is full of mysteries waiting to be uncovered. Whether wormholes lead to distant stars, alternate timelines, or entirely different realities, they represent the ultimate frontier of exploration, pushing the boundaries of what we thought was possible. As we continue to explore these ideas, we're not just imagining new ways to travel, we're redefining what it means to exist in a cosmos that might be far vaster and more interconnected than we ever dared to dream. And with each new discovery, we move one step closer to understanding the true nature of reality itself. Now, let's shift our focus to another intriguing question. What if wormholes aren't just theoretical constructs, but actual features of the universe? Could they exist naturally, hidden in the depths of space, waiting to be discovered? Let's explore that next. While the idea of traveling through a wormhole is undeniably thrilling, it's not without its dangers. Imagine stepping into a cosmic tunnel, only to be stretched like a piece of spaghetti or bombarded by lethal radiation. These are just some of the risks that come with traversing a wormhole, and they remind us that even the most promising shortcuts through the universe come with serious challenges. One of the most immediate dangers is spaghettification, a term that sounds almost comical but describes a very real and terrifying phenomenon. As you approach the entrance of a wormhole, the gravitational forces become so intense that they stretch your body into a long, thin strand like spaghetti. This happens because the pull of gravity is much stronger at your feet than at your head, creating a tidal force that literally pulls you apart. For smaller wormholes, this effect would be instantaneous and fatal. Even for larger, more stable wormholes, the tidal forces could still pose a significant threat, requiring advanced shielding or propulsion systems to counteract them. But spaghettification isn't the only hazard. Wormholes could also expose travelers to intense radiation. As matter and energy are funneled through the wormhole's throat, they could generate high-energy particles and electromagnetic waves capable of frying electronics or worse, living tissue. This radiation could come from the surrounding environment, such as nearby stars or black holes, or it could be produced by the wormhole itself as it warps spacetime. Without proper protection, a journey through a wormhole could be as deadly as it is exciting. So, how could we mitigate these risks? One possibility lies in advanced technology. For example, a spacecraft equipped with powerful magnetic fields or energy shields might be able to deflect radiation and stabilize the environment inside the wormhole. Similarly, propulsion systems that counteract gravitational forces could help prevent spaghettification, allowing travelers to pass through safely. These technologies are still far beyond our current capabilities, but they're not beyond the realm of possibility. As our understanding of physics and engineering advances, so too might our ability to navigate the dangers of wormhole travel. Beyond the immediate risks, wormholes also raise intriguing questions about the nature of spacetime itself. Could the extreme conditions inside a wormhole reveal new insights into gravity, quantum mechanics, or even the origins of the universe? Some physicists believe that studying wormholes could help us solve some of the greatest cosmic mysteries, from the behavior of black holes to the nature of dark energy. In this sense, wormholes aren't just potential shortcuts through space, they're also windows into the fundamental laws that govern reality. As we continue to explore these ideas, we're reminded that the pursuit of knowledge often comes with risks and rewards. Wormholes represent both the extraordinary potential of human ingenuity and the profound challenges of exploring the unknown. And while the dangers are real, so too is the promise of discovery, a promise that drives us to push the boundaries of what's possible, both in the cosmos and within ourselves. Now, let's turn our attention to another fascinating question. What if wormholes aren't just tools for travel, but also keys to understanding the universe's deepest secret? Let's explore that next. What if the reason we haven't found extraterrestrial civilizations isn't because they don't exist, but because they've mastered wormholes? This intriguing possibility offers a fresh perspective on the Fermi Paradox, the puzzling question of why, in a universe so vast and ancient, we haven't encountered any signs of intelligent life beyond Earth. The paradox, named after physicist Enrico Fermi, highlights the contradiction between the high probability of alien civilizations existing and the complete lack of evidence for their existence. But what if wormholes hold the key to solving this cosmic mystery? One compelling theory suggests that advanced civilizations might have developed wormhole technology, allowing them to travel across the universe without leaving detectable traces. Imagine a civilization millions or even billions of years ahead of us, with the ability to manipulate spacetime itself. Instead of relying on slow, energy-intensive methods like rockets or light sails, they could use wormholes as cosmic highways, bypassing the limitations of distance and time. This would make their movements virtually invisible to us, as they wouldn't need to emit the kind of signals like radio waves or heat signatures that we typically search for. But there's another layer to this idea. If wormholes are indeed being used by advanced civilizations, they might not just be tools for travel, they could also serve as cosmic recycling mechanisms. Picture this: a civilization that has reached the pinnacle of technological development might use wormholes to harvest energy or resources from distant parts of the universe, or even from other universes entirely. By funneling matter and energy through wormholes, they could sustain their societies indefinitely, all while remaining hidden from less advanced species like us. This concept raises fascinating questions about the nature of intelligence and progress. If wormholes are the ultimate form of travel and resource management, It's possible that civilizations that master them simply have no need to broadcast their presence. They might operate in ways that are completely beyond our current understanding, leaving no detectable footprint in the cosmos. In this scenario, the Fermi Paradox isn't a sign of our loneliness, it's a reflection of our technological infancy. Of course, this is just one possible explanation among many. The Fermi Paradox remains one of the most enduring mysteries in science, and wormholes are just one piece of the puzzle. But the idea that advanced civilizations might be using wormholes to navigate the universe, and perhaps even recycle its resources, offers a tantalizing glimpse into what might be possible in the far reaches of space and time. As we ponder these possibilities, we're reminded that the universe is full of secrets waiting to be uncovered. Whether wormholes are the key to solving the Fermi Paradox or simply another piece of the cosmic puzzle, they challenge us to think bigger, to imagine a reality where the boundaries of space, time, and intelligence are far more fluid than we ever dreamed. Now, let's shift our focus to another intriguing question. What if wormholes aren't just tools for travel or resource management, but also mechanisms for cosmic recycling on a grand scale? Let's explore that next. What if the universe itself is caught in an endless loop of creation and destruction, with wormholes acting as the cosmic thread stitching it all together? This is the mind-bending idea behind the theory that wormholes could play a key role in the cyclical nature of the universe, connecting the end of one cosmic cycle to the beginning of another. It's a concept that challenges our understanding of time, space, and the very origins of existence. At the heart of this theory is the idea that the universe might not have a single beginning or end. Instead, it could be part of an infinite cycle, a series of big bangs and big crunches where the universe expands, contracts, and then explodes into existence once more. In this model, wormholes could serve as the bridges between these cycles, funneling matter and energy from the dying universe into the newborn one. Imagine the final moments of a collapsing universe where everything is pulled into a singularity. Instead of vanishing into nothingness, that singularity could connect to a wormhole, transporting the remnants of the old universe into the next Big Bang. This idea isn't just speculative, it's rooted in some of the most advanced theories in physics, including quantum gravity and string theory. Quantum gravity seeks to reconcile the laws of general relativity, which govern the large-scale structure of the universe, with the rules of quantum mechanics, which describe the behavior of particles at the smallest scales. Wormholes, with their ability to warp spacetime and connect distant points, could be the missing link that ties these two realms together. One of the most intriguing implications of this theory is that it could explain the origins of the Big Bang itself. If wormholes connect the end of one cosmic cycle to the beginning of another, then the Big Bang might not have been a singular event, but rather the latest in an endless series of cosmic rebirths. This would mean that our universe is just one chapter in an infinite story, with wormholes acting as the narrative thread that ties it all together. But how could wormholes survive the extreme conditions of a collapsing universe? Some physicists suggest that quantum effects could stabilize wormholes even in the face of such immense gravitational forces. At the quantum level, particles can tunnel through barriers that would be impossible to overcome in classical physics. If wormholes are governed by similar principles, they might remain intact even as the universe collapses around them, providing a pathway for matter and energy to escape into the next cycle. This cyclical model of the universe also raises profound questions about the ultimate fate of existence. If the universe is caught in an endless loop, does that mean everything is destined to repeat itself? Could the same stars, planets, and even civilizations arise again and again, trapped in an eternal cosmic dance? Or would each cycle bring something entirely new, with the laws of physics subtly shifting each time? While these questions remain unanswered, the idea of wormholes as cosmic recycling mechanisms offers a fascinating perspective on the nature of reality. It suggests that the universe might be far more interconnected and far more resilient than we ever imagined. And as we continue to explore these theories, we're not just uncovering the secrets of wormholes, we're redefining what it means to exist in a cosmos that might be infinitely more complex and wondrous than we ever dared to dream. Now, let's turn our attention to another intriguing question. What role do wormholes play in the quest to unify quantum mechanics and gravity? Could they hold the key to solving one of the greatest mysteries in physics? Let's dive deeper into that next. What if wormholes aren't just shortcuts through space, but also bridges between the two most fundamental theories in physics? Quantum mechanics and general relativity are the twin pillars of modern physics, yet they've stubbornly resisted unification for over a century. Quantum mechanics governs the behavior of particles at the smallest scales, while general relativity describes the large-scale structure of spacetime. But when it comes to understanding the universe as a whole, these two theories seem to speak entirely different languages. Enter wormholes, hypothetical tunnels through spacetime that might just hold the key to bridging this gap. At the heart of this challenge is the fact that quantum mechanics and general relativity operate under completely different rules. Quantum mechanics thrives on uncertainty, probability, and the bizarre behavior of particles at the smallest scales. General relativity, on the other hand, paints a smooth, deterministic picture of spacetime, where gravity is the curvature caused by mass and energy. When these two theories collide, like at the center of a black hole or during the Big Bang physics as we know it breaks down, this is where wormholes come in. Some of the most promising theories of quantum gravity, such as string theory and loop quantum gravity, suggest that wormholes could play a crucial role in reconciling these two frameworks. String theory, for example, proposes that the fundamental building blocks of the universe aren't particles but tiny, vibrating strings. These strings exist in higher dimensional spaces, and wormholes could be the threads that connect these dimensions, weaving together the quantum and cosmic realms. Loop quantum gravity, another leading theory, takes a different approach. It suggests that spacetime itself is made up of discrete, quantized loops, like a cosmic fabric woven from tiny threads. In this view, wormholes could be the natural bridges between these loops, creating pathways that allow information and energy to flow seamlessly between the quantum and relativistic worlds. But how exactly could wormholes help unify these theories? One possibility lies in their ability to act as information highways. In quantum mechanics, information is never lost, it's always conserved, even in the most extreme conditions. But in general relativity, information can seemingly vanish into a black hole, leading to the infamous information paradox. Wormholes might offer a solution. If information can travel through wormholes, it could escape a black hole's grasp, preserving the principles of quantum mechanics while respecting the laws of general relativity. This idea is at the core of the ER=EPR conjecture, which we touched on earlier. It suggests that entangled particles, those spooky, instantaneously connected pairs, might be linked by microscopic wormholes. In this view, quantum entanglement isn't just a mathematical quirk, it's a physical connection through space-time. This would mean that wormholes aren't just cosmic shortcuts, they're fundamental to the very fabric of reality, stitching together the quantum and cosmic scales in ways we're only beginning to understand. The implications of this are profound. If wormholes can bridge the gap between quantum mechanics and general relativity, they might help us solve some of the deepest mysteries in physics, from the nature of black holes to the origins of the universe itself. They could also open up new possibilities for technology, allowing us to harness the power of quantum gravity in ways we can't yet imagine. As we continue to explore these ideas, we're reminded that the universe is far more interconnected and far more mysterious than we ever realized. Wormholes aren't just tools for travel or windows into other dimensions. They're potential keys to unlocking the secrets of existence itself. And with each new discovery, we move one step closer to understanding the true nature of reality. Now, let's turn our attention to another fascinating question. What if wormholes aren't just bridges between theories, but also highways for information itself? Could they hold the key to solving the black hole information paradox? Let's dive deeper into that next. What happens to information when it falls into a black hole? This question lies at the heart of one of the most perplexing mysteries in physics, the black hole information paradox. According to quantum mechanics, information can never be destroyed. It's always conserved, no matter what. But black holes, with their immense gravitational pull, seem to defy this rule. Anything that crosses a black hole's event horizon is lost forever, or so it seems. This contradiction has puzzled physicists for decades, but wormholes might hold the key to solving it. The paradox arises because black holes don't just swallow matter, they also consume information. Imagine throwing a book into a black hole. The book is made of atoms, and those atoms carry information about its contents. According to quantum mechanics, that information should still exist somewhere, even if the book itself is destroyed. But general relativity suggests that the information is irretrievably lost, vanishing into the black hole's singularity. This clash between the two theories has left physicists scratching their heads, searching for a way to reconcile them. Enter wormholes. Some theories propose that information swallowed by a black hole doesn't disappear. It escapes through a wormhole. Picture this: as the book falls into the black hole, its information is encoded in the fabric of spacetime, funneled through a wormhole, and then re-emerges somewhere else in the universe. This would mean that the information isn't lost, it's just transported to a new location, preserving the principles of quantum mechanics while respecting the laws of general relativity. This idea is at the core of the EPR conjecture, which we've touched on earlier. It suggests that entangled particles, those spooky, instantaneously connected pairs, might be linked by microscopic wormholes. In this view, quantum entanglement isn't just a mathematical quirk, it's a physical connection through spacetime. If true, this would mean that wormholes aren't just cosmic shortcuts, they're fundamental to the very fabric of reality, stitching together the quantum and cosmic scales in ways we're only beginning to understand. But how could this work in practice? One possibility is that wormholes act as information highways, allowing data to bypass the black hole's singularity and escape into another part of the universe. This would mean that black holes aren't the ultimate dead ends we once thought. They might be more like cosmic recycling centers, where information is processed and redistributed rather than destroyed. The implications of this are profound. If wormholes can preserve information, they might help us solve the black hole information paradox, one of the greatest unsolved problems in physics. But they could also revolutionize how we think about communication. Imagine a future where we could send information through wormholes, transmitting data across the universe instantaneously. This wouldn't just change how we explore space, it could transform how we connect with each other, creating a network of cosmic communication that spans galaxies. Of course, this is still firmly in the realm of theory. We don't yet know if wormholes exist, let alone whether they could carry information. But the idea that they might hold the key to solving the black hole information paradox is a reminder of how interconnected the universe might be. It suggests that the answers to some of our deepest questions could lie in the most unexpected places, hidden within the fabric of spacetime itself. As we continue to explore these ideas, we're not just uncovering the secrets of wormholes, we're redefining what it means to understand the universe. And with each new discovery, we move one step closer to solving the mysteries that have puzzled us for generations. Now, let's turn our attention to another intriguing possibility. What if wormholes aren't just tools for preserving information, but also mechanisms for instantaneous communication across the cosmos? Let's explore that next. What if the ultimate communication network wasn't built on satellites or fiber optics, but on wormholes? Imagine a future where messages could travel instantaneously across the universe, bypassing the limitations of distance and time. This isn't just a sci-fi dream, it's a tantalizing possibility rooted in the theoretical foundations of wormholes. If these cosmic tunnels could be stabilized and harnessed, they might revolutionize how civilizations communicate, creating a web of instantaneous connections that spans galaxies. The idea hinges on the concept that wormholes could act as information highways. Just as they might allow matter to travel vast distances in an instant, they could also transmit data. Picture this: a message sent into one end of a wormhole emerges from the other end almost immediately, regardless of how far apart the 2 points are. This would mean that communication between planets, stars, or even galaxies could happen in real time, eliminating the delays that currently make interstellar communication so challenging. But how could this work in practice? One possibility is that wormholes could be used to create a network of quantum entanglement relays. Quantum entanglement, as we've discussed, links particles in such a way that the state of one instantly influences the other, no matter the distance. If wormholes are indeed the physical manifestation of these entangled connections, they could serve as the backbone of a cosmic communication system. Messages encoded in quantum states could be sent through wormholes, allowing for instantaneous transmission across the universe. The implications of this are staggering. For interstellar civilizations, wormhole-based communication could enable the exchange of knowledge, culture, and technology on an unprecedented scale. Imagine a galactic internet where civilizations separated by thousands of light years could share ideas and collaborate in real time. This wouldn't just transform how we explore space, it could redefine what it means to be part of a connected universe. But wormholes might also hold the key to solving one of the greatest mysteries in science: the search for extraterrestrial life. If advanced civilizations are using wormholes for communication, they might leave behind subtle clues that we could detect. For example, the energy signatures of stabilized wormholes or the quantum signals they transmit could serve as markers of intelligent life. This would give us a new way to search for extraterrestrial civilizations, not by looking for radio waves or megastructures, but by hunting for the cosmic fingerprints of wormhole networks. This idea ties back to the Fermi Paradox, the question of why we haven't found evidence of alien life despite the vastness of the universe. If advanced civilizations are using wormholes for communication and travel, they might be operating in ways that are completely invisible to us. Their signals could be encoded in quantum states or transmitted through wormholes, making them undetectable by our current technology. In this scenario, the reason we haven't found extraterrestrial life isn't because it doesn't exist, it's because we're looking in the wrong way. The potential for wormholes as communication channels opens up a new frontier in our search for intelligent life. It challenges us to think beyond traditional methods and consider the possibility that the universe is teeming with civilizations that are far more advanced and far more connected than we ever imagined. And as we continue to explore these ideas, we're not just dreaming of a future where we can talk to the stars, we're redefining what it means to be part of a cosmic community. Now, let's shift our focus to another intriguing question. What if wormholes aren't just tools for communication, but also windows into the very nature of reality itself? Could they hold the key to understanding the universe's deepest secrets? Let's explore that next. What if the key to finding extraterrestrial life isn't just about building better telescopes, but about discovering wormholes? These cosmic shortcuts could revolutionize the search for life beyond Earth, offering pathways to distant star systems and potentially habitable planets that are currently out of reach. Imagine a future where we don't just peer at distant worlds through a lens, but step through a wormhole to explore them up close. The implications for astrobiology, the study of life in the universe, are staggering. Wormholes could provide access to regions of the cosmos that are otherwise inaccessible due to the vast distances involved. For example, the nearest potentially habitable exoplanet, Proxima Centauri b, is over 4 light-years away. Even with our most advanced propulsion systems, reaching it would take thousands of years. But if a wormhole connected Earth to Proxima Centauri b, the journey could be instantaneous. This would open up entirely new possibilities for exploration, allowing us to study alien ecosystems, search for signs of life, and even establish contact with extraterrestrial civilizations. But wormholes might do more than just shorten the distance. They could also help us identify the most promising targets for exploration. Advanced civilizations, if they exist, might use wormholes as cosmic highways, creating networks that connect habitable planets across the galaxy. By detecting the energy signatures or gravitational effects of these wormholes, we could pinpoint regions of space where life is most likely to thrive. This would give us a roadmap for exploration, guiding us to the most promising candidates for finding extraterrestrial life. Of course, the discovery of wormholes wouldn't just be a scientific breakthrough, it would also raise profound ethical questions. If we found a wormhole leading to a distant star system, how should we approach it? Should we send probes through first to assess the risks, or would we be compelled to explore it ourselves? And what if we encountered intelligent life on the other side? How would we communicate, and what responsibilities would we have as visitors to their world? These are the kinds of questions that would shape the future of interstellar exploration, challenging us to think not just about the science, but also about the ethics of venturing into the unknown. The search for extraterrestrial life has always been about more than just curiosity. It's about understanding our place in the universe. Wormholes could bring us closer to answering that question, offering a way to explore the cosmos that was once the stuff of science fiction. But as we take these first steps into the unknown, we'll need to balance our ambition with caution, ensuring that our quest for knowledge doesn't come at the expense of the worlds we seek to discover. Now, let's turn our attention to another intriguing possibility. What if wormholes aren't just tools for exploration, but also mechanisms for preserving the diversity of life in the universe? Could they play a role in safeguarding civilizations from cosmic threats? Let's explore that next. What if the ability to travel through wormholes became a reality, but only for a select few? This isn't just a question of technology, it's a profound ethical dilemma. As we dream of stepping through cosmic shortcuts to explore distant stars, we must also confront the challenges of access, equity, and the potential for exploitation. Who gets to travel through wormholes and who decides? These are the questions that could shape the future of interstellar exploration, forcing us to grapple with the moral implications of our cosmic ambitions. The idea of wormhole travel raises immediate concerns about fairness. If wormholes are as rare and resource-intensive as current theories suggest, they might only be accessible to the wealthiest nations, corporations, or individuals. This could create a new kind of cosmic divide, where the privileged few have the power to explore and colonize distant worlds, while the rest of humanity is left behind. Imagine a future where entire star systems are claimed by private entities, their resources exploited for profit, and their ecosystems altered without regard for the broader consequences. The ethical implications are staggering, and they demand careful consideration as we move closer to making wormhole travel a reality. But the challenges don't end there. Even if access to wormholes were democratized, there's the question of how to manage the risks. Wormhole travel could expose travelers to extreme dangers, from spaghettification to lethal radiation. Who would be responsible for ensuring the safety of those who venture through? Would governments regulate wormhole travel, or would it fall to private companies? And what happens if something goes wrong, if a wormhole collapses, or if travelers encounter hostile environments on the other side? These are the kinds of questions that could spark intense debate, forcing us to balance the promise of exploration with the need for caution and accountability. Beyond the practical and ethical concerns, there's also the question of how wormhole travel could impact the societies we encounter. If we discover intelligent life on the other side of a wormhole, how should we interact with it? Would we approach these civilizations as equals, or would we risk repeating the mistakes of colonialism, imposing our values and systems on others? The history of human exploration is filled with examples of exploitation and conflict, and we must ensure that our journey into the cosmos doesn't follow the same path. Navigating these challenges will require more than just technological innovation. It will demand a global conversation about the values we want to carry into the stars. Should wormhole travel be governed by international treaties, ensuring that its benefits are shared equitably? Could we establish ethical guidelines for exploration, prioritizing scientific discovery and mutual respect over profit and power? These are the questions that will define the future of interstellar travel, and they remind us that the journey into the cosmos is as much about who we are as it is about where we're going. As we grapple with these ethical dilemmas, it's worth remembering that wormholes aren't just tools for travel, they are also gateways to scientific discovery. By studying wormholes, we could unlock some of the deepest mysteries of the universe, from the nature of spacetime to the origins of existence itself. This potential for knowledge adds another layer to the ethical debate, highlighting the importance of ensuring that wormhole exploration serves the greater good. The ethics of wormhole travel are complex, but they're also an opportunity, a chance to redefine what it means to explore, to connect, and to grow as a species. As we stand on the brink of this new frontier, we have the power to shape a future that reflects our highest ideals, one where the stars are not just a destination but a shared journey. Now, let's shift our focus to another fascinating question. What if wormholes aren't just tools for travel or ethical dilemmas, but also keys to unlocking the universe's greatest scientific mysteries? Let's explore that next. What if wormholes could do more than just transport us across the cosmos? What if they could also unlock the deepest secrets of the universe itself? These cosmic shortcuts aren't just tools for travel, they're potential windows into the fundamental nature of reality. By allowing us to study distant regions and phenomena firsthand, wormholes could revolutionize our understanding of physics, astronomy, and even the origins of existence. Imagine stepping through a wormhole to observe the birth of a star, the collision of galaxies, or the mysterious behavior of dark matter. The possibilities for discovery are as vast as the universe itself. One of the most exciting prospects is the ability to study black holes up close. Black holes are some of the most enigmatic objects in the cosmos, with gravitational fields so intense that not even light can escape. But what happens inside a black hole? What lies beyond the event horizon? These are questions that have puzzled scientists for decades, and wormholes could provide the answers. By creating a stable pathway into or around a black hole, we could gather data that's currently impossible to obtain, shedding light on the nature of singularities, the behavior of spacetime under extreme conditions, and even the fate of information that falls into a black hole. Wormholes could also give us a front-row seat to some of the universe's most dramatic events. Take gamma-ray bursts, for example, enormous explosions that release more energy in a few seconds than the sun will emit in its entire lifetime. These bursts are thought to occur during the collapse of massive stars or the collision of neutron stars, but their exact mechanisms remain a mystery. By using wormholes to observe these events in real time, we could gain unprecedented insights into the life cycles of stars and the forces that shape the cosmos. But the potential for discovery doesn't stop there. Wormholes could also help us unravel the mysteries of dark energy and dark matter, the invisible forces that make up most of the universe. Dark energy is driving the accelerated expansion of the cosmos, while dark matter's gravitational pull holds galaxies together. Yet, despite their profound influence, we know almost nothing about them. Wormholes could provide a way to study these elusive phenomena directly, offering clues about their nature and how they shape the universe on the largest scales. Beyond physics and astronomy, wormholes could also transform our understanding of biology and evolution. Imagine traveling through a wormhole to a distant planet with a completely different environment, one with higher gravity, a different atmosphere, or even alternate forms of life. By studying how organisms adapt to these conditions, we could gain new insights into the processes that drive evolution and the potential for life to thrive in extreme environments. This could even help us prepare for the challenges of colonizing other worlds, ensuring that humanity can survive and thrive beyond Earth. The role of wormholes in human evolution could be equally profound. As we venture into the cosmos, our species will face new challenges and opportunities that could shape our future in ways we can't yet imagine. Wormholes could accelerate this process, allowing us to explore and adapt to new environments far more quickly than would otherwise be possible. This could lead to the emergence of new traits, technologies, and even cultures, fundamentally altering the trajectory of human history. As we continue to explore these ideas, it's clear that wormholes aren't just shortcuts through space, they're gateways to a deeper understanding of the universe and our place within it. By unlocking their secrets, we could uncover answers to some of the greatest questions in science, from the nature of black holes to the origins of life itself. And as we stand on the brink of this new frontier, we're reminded that the journey into the cosmos is as much about discovery as it is about exploration. Now, let's turn our attention to another fascinating possibility. What if wormholes aren't just tools for scientific discovery, but also mechanisms for preserving the diversity of life in the universe? Could they play a role in safeguarding civilizations from cosmic threats? Let's explore that next. What if wormholes aren't just tools for exploration, but also catalysts for the next great leap in human evolution? As we stand on the brink of becoming an interstellar species, the ability to traverse wormholes could fundamentally reshape who we are and how we exist. Imagine a future where humanity isn't confined to a single planet, but spreads across the stars, adapting to new environments, cultures, and challenges. This isn't just about survival, it's about transformation. Wormholes could be the key to unlocking a new chapter in our evolutionary story, one where we evolve not just biologically, but culturally and technologically as well. The journey to becoming an interstellar species would push humanity to its limits. Living on distant planets with different gravities, atmospheres, and ecosystems would force us to adapt in ways we can't yet fully imagine. Over generations, these adaptations could lead to the emergence of new traits, perhaps stronger bones to withstand higher gravity, or enhanced lung capacity to breathe thinner air. But evolution isn't just physical, it's also cultural. As we encounter alien worlds and civilizations, our understanding of art, science, and philosophy could expand in ways that redefine what it means to be human. Wormholes could accelerate this process by making interstellar travel not just possible but practical. Instead of spending centuries traveling between stars, we could step through a wormhole and arrive in an instant. This would allow us to establish colonies, share knowledge, and build connections across the galaxy far more quickly than we ever could with traditional propulsion systems. The result, a thriving, interconnected interstellar civilization where ideas and innovations flow freely, and humanity evolves not in isolation but as part of a vast cosmic community. But the implications go even deeper. Wormholes could also play a crucial role in ensuring the long-term survival of our species. Earth, for all its beauty, is fragile. Climate change, asteroid impacts, and other existential threats remind us that our future here is far from guaranteed. By spreading across the stars, we could safeguard humanity against these risks, ensuring that even if one world falls, countless others remain. Wormholes would make this vision achievable, turning the dream of a multi-planetary species into a tangible reality. And then there's the question of what we might become. As we explore the cosmos, we'll encounter challenges and opportunities that could reshape our identity. Will we remain recognizably human, or will we evolve into something entirely new? Could wormholes lead us to merge with advanced technologies, becoming a hybrid species that transcends the limits of biology? These are the kinds of questions that wormhole travel forces us to confront, challenging us to imagine a future where humanity is no longer bound by the constraints of a single planet. As we ponder these possibilities, it's worth considering another dimension of wormholes: their potential as cosmic art. Imagine a wormhole not just as a tool for travel, but as a canvas for creativity. The way it warps space-time, bending light and gravity into mesmerizing patterns, could inspire new forms of artistic expression. Artists and scientists alike might collaborate to create wormhole-inspired installations, blending the beauty of the cosmos with the ingenuity of human imagination. In this way, wormholes could become more than just pathways. They could be symbols of our boundless creativity and our unyielding drive to explore the unknown. The journey through wormholes isn't just about reaching new worlds. It's about discovering new possibilities for who we are and what we can become. As we take these first steps into the cosmos, we're not just exploring space, we're redefining the very essence of humanity. And with each new discovery, we move closer to a future where the stars are not just a destination, but a shared journey of evolution and growth. Now, let's shift our focus to another intriguing possibility. What if wormholes aren't just tools for travel or evolution, but also gateways to a new form of cosmic art? Let's explore that next. What if wormholes weren't just scientific marvels, but also masterpieces of cosmic art? Picture a wormhole not as a cold mathematical construct, but as a swirling, luminous tunnel of spacetime, bending light and gravity into mesmerizing patterns. The sheer beauty of such a phenomenon could rival the most stunning natural wonders, from the auroras dancing in Earth's atmosphere to the swirling storms on Jupiter. Wormholes, with their ability to warp reality itself, could inspire awe and wonder, reminding us that the universe is as much a canvas of creativity as it is a laboratory of physics. This aesthetic appeal isn't just theoretical, it's already captured the imagination of artists and storytellers. From the shimmering portals in science fiction films to the surreal landscapes painted by visionary artists, wormholes have become symbols of the infinite possibilities of the cosmos. They represent not just a way to travel, but a gateway to the unknown, a visual metaphor for the mysteries that lie beyond our understanding. In this way, wormholes transcend their scientific roots, becoming a source of inspiration that bridges the gap between art and science. The philosophical implications are equally profound. Wormholes challenge our perception of reality, forcing us to confront questions about the nature of space, time, and existence itself. What does it mean to step through a tunnel that connects distant points in the universe? Could such an act change our understanding of identity, connection, and the passage of time? These are the kinds of questions that wormholes provoke, inviting us to think not just about the mechanics of the cosmos, but about the deeper meaning of our place within it. Science fiction has long embraced these ideas, using wormholes as a narrative device to explore the boundaries of human imagination. In films like Interstellar and Contact, wormholes serve as gateways to new worlds and new possibilities, offering a glimpse of what might lie beyond the stars. These stories remind us that wormholes aren't just tools for travel. They're symbols of hope, curiosity, and the unyielding human desire to explore the unknown. But the influence of wormholes extends beyond the screen. They've inspired countless works of literature, from the mind-bending novels of Arthur C. Clarke to the poetic musings of Carl Sagan. In these stories, wormholes are more than just plot devices. They're reflections of our deepest fears and aspirations, mirrors that show us both the limits of our knowledge and the boundless potential of our imagination. This interplay between science and art is a reminder that the universe is not just a place to be studied, but a source of endless inspiration. Wormholes, with their blend of beauty and mystery, embody this duality, inviting us to see the cosmos not just as a collection of equations, but as a living, breathing work of art. And as we continue to explore these ideas, we're reminded that the journey into the unknown is as much about creativity as it is about discovery. Now, let's shift our focus to another fascinating question. What if wormholes aren't just tools for travel or sources of inspiration, but also keys to unlocking the universe's greatest scientific mysteries? Let's explore that next. Science fiction has long been a playground for the imagination, and wormholes have taken center stage in some of the most iconic stories ever told. From the silver screen to the pages of novels, these cosmic shortcuts have captured our collective imagination, offering a tantalizing glimpse of what might be possible. Take Interstellar, for example. Christopher Nolan's epic film brought wormholes to life with stunning visuals and a gripping narrative, portraying them as gateways to distant galaxies and humanity's last hope for survival. The film's depiction of a wormhole near Saturn with its shimmering, spherical surface wasn't just a visual masterpiece, it was rooted in real science, thanks to the guidance of physicist Kip Thorne. This blend of art and science made Interstellar a landmark in how wormholes are portrayed, sparking both wonder and curiosity in audiences worldwide. But Interstellar is just one example. Wormholes have been a staple of science fiction for decades, appearing in everything from Star Trek to Stargate. In Star Trek: Deep Space Nine, the Bajoran wormhole serves as a vital link between distant regions of space, enabling exploration, trade, and even conflict. It's not just a plot device, it's a symbol of connection, bridging cultures and civilizations across the cosmos. Similarly, Stargate uses wormholes as literal portals, allowing characters to step through a ring-shaped device and emerge on alien worlds. These stories have shaped how we think about wormholes, turning them from abstract mathematical concepts into vivid, tangible possibilities. The influence of science fiction goes beyond entertainment. It has also inspired real scientific inquiry. The idea of wormholes as cosmic shortcuts has motivated physicists to explore whether such phenomena could exist in reality. For instance, the concept of traversable wormholes, popularized by Kip Thorne's work, was partly inspired by the imaginative portrayals in science fiction. These stories have sparked public interest, driving funding and research into areas that might otherwise have been overlooked. In a way, science fiction has acted as a bridge between the abstract world of theoretical physics and the everyday curiosity of the general public. However, turning fiction into reality is no small feat. While science fiction often glosses over the technical challenges, real-world wormholes come with a host of obstacles. The need for exotic matter, the immense energy requirements, and the instability of wormholes are just a few of the hurdles scientists face. And then there's the question of whether wormholes could ever be safe or practical for travel. Could a human survive the journey through a wormhole, or would the extreme gravitational forces tear them apart? These are the kinds of questions that science fiction rarely addresses, but they're crucial for turning the dream of wormhole travel into a reality. Despite these challenges, the influence of science fiction remains undeniable. It has shaped how we envision the future, inspiring generations to dream of exploring the stars. And while the wormholes of Interstellar and Star Trek may still be out of reach, they remind us that the line between imagination and reality is often thinner than we think. As we continue to push the boundaries of science, who knows, the wormholes of tomorrow might just be as extraordinary as the ones we've dreamed up on screen. Now, let's shift our focus to another intriguing question. What if wormholes aren't just tools for travel or inspiration, but also keys to unlocking the universe's greatest scientific mysteries? Let's explore that next. The dream of wormholes as cosmic shortcuts is undeniably thrilling, but turning that dream into reality comes with a mountain of challenges. While the math might suggest that wormholes are possible, the practical hurdles of studying, let alone creating one, are immense. From technological limitations to the sheer scale of resources required, the path from theory to practice is anything but straightforward. First, there's the issue of technology. To even begin experimenting with wormholes, we'd need tools and instruments far beyond what we currently have. For example, stabilizing a wormhole would require exotic matter with negative energy, something we've never observed, let alone produced. Even if we could create it, the energy demands would be astronomical. Some estimates suggest that stabilizing a wormhole large enough for human travel would require energy equivalent to the output of an entire star. That's not just a technological challenge, it's a logistical one, requiring breakthroughs in energy generation, storage, and efficiency that we can't yet imagine. Then there's the question of funding. Wormhole research sits at the intersection of theoretical physics and cutting-edge engineering, and both fields require significant investment. Building the infrastructure to test wormhole theories, whether it's particle accelerators, space-based observatories, or advanced computational models, would cost billions of dollars. Securing that kind of funding is no small feat, especially when the practical applications of wormholes are still decades, if not centuries, away. Governments, private companies, and international organizations would all need to come together to make this a priority, and that level of collaboration is easier said than done. Speaking of collaboration, wormhole research would require unprecedented global cooperation. This isn't just a project for one country or institution. It's a challenge that would need the combined efforts of scientists, engineers, and policymakers from around the world. Think of it like the International Space Station, but on a much larger scale. Sharing data, resources, and expertise would be essential, but it would also require navigating complex political and cultural differences. The success of wormhole research would depend not just on scientific breakthroughs, but on our ability to work together as a global community. Despite these challenges, the future of wormhole research is far from bleak. In fact, the very obstacles we face could drive innovation in unexpected ways. For example, the search for exotic matter might lead to new discoveries in quantum physics or materials science. The energy requirements could spur advancements in renewable energy or fusion technology, and the need for international collaboration could foster a new era of global cooperation, uniting humanity in a shared quest to explore the cosmos. Looking ahead, the next steps in wormhole research will likely focus on smaller, more manageable goals. Instead of aiming for a fully traversable wormhole right away, scientists might start by testing the principles of wormhole stability on a microscopic scale. Quantum experiments, for instance, could help us understand how exotic matter behaves or how spacetime can be manipulated. These small steps might not lead to interstellar travel anytime soon, but they could lay the groundwork for future breakthroughs. The journey from theory to practice is never easy, but it's often where the most exciting discoveries are made. Wormholes represent one of the greatest challenges and opportunities in modern science. By tackling the practical hurdles head-on, we're not just chasing a dream, we're pushing the boundaries of what's possible, both for humanity and for our understanding of the universe. Now let's shift our focus to the future of wormhole research and the incredible possibilities it holds. What might the next century of exploration look like, and how could wormholes reshape our place in the cosmos? Let's explore that next. As we look to the future of wormhole research, the possibilities are as vast as the cosmos itself. The journey from theoretical curiosity to practical reality is filled with challenges, but it's also brimming with potential. Advances in technology, breakthroughs in theoretical physics, and the tantalizing prospect of experimental verification are all on the horizon, promising to bring us closer to understanding and perhaps even harnessing these cosmic shortcuts. One of the most exciting areas of progress lies in quantum computing. These powerful machines, still in their infancy, could revolutionize how we model and simulate wormholes. By leveraging the principles of quantum mechanics, we might be able to explore the behavior of exotic matter, test the stability of wormhole geometries, and even simulate the effects of traversing one. While we're not yet at the point of creating a wormhole in a lab, quantum simulations could provide invaluable insights, helping us refine our theories and identify the most promising paths forward. Another frontier is the development of advanced telescopes and observational tools. Projects like the James Webb Space Telescope and future gravitational wave detectors could offer new ways to search for evidence of wormholes in the universe. For example, if a wormhole were to pass between Earth and a distant star, its gravitational lensing effect might create a unique signature in the star's light. Detecting such a signal would be a monumental achievement, providing the first observational evidence that wormholes exist. On the theoretical side, physicists are exploring new frameworks that could make wormholes more feasible. Some researchers are investigating whether modifications to general relativity or new insights from string theory could eliminate the need for exotic matter, making wormholes easier to stabilize. Others are delving into the quantum realm, studying how phenomena like entanglement and superposition might be harnessed to create or manipulate wormholes. These efforts are pushing the boundaries of our understanding, revealing connections between seemingly unrelated areas of physics. But the future of wormhole research isn't just about science, it's also about collaboration. The challenges we face are too great for any one nation or institution to tackle alone. International partnerships, like those behind the Large Hadron Collider or the Event Horizon Telescope, will be essential. By pooling resources, expertise, and creativity, we can accelerate progress and turn what once seemed like science fiction into science fact. The implications of successful wormhole research extend far beyond the realm of physics. If we could create or discover a stable wormhole, it would fundamentally alter our relationship with the universe. Interstellar travel, once the stuff of dreams, could become a reality, opening up new frontiers for exploration and colonization. The search for extraterrestrial life could take on a whole new dimension, as wormholes might provide pathways to distant star systems teeming with potential. And on a philosophical level, the existence of wormholes would challenge our understanding of space, time, and the very nature of reality. As we stand on the brink of these possibilities, it's worth reflecting on what drives us to explore the unknown. Wormholes represent more than just a scientific challenge. They're a symbol of humanity's unyielding curiosity and our desire to push the boundaries of what's possible. Whether we're peering into the quantum realm or gazing at distant galaxies, the pursuit of knowledge reminds us that the universe is full of wonders waiting to be discovered. The future of wormhole research is as uncertain as it is exciting, but one thing is clear: the journey ahead will be as transformative as the destination. As we continue to explore these cosmic mysteries, we're not just unlocking the secrets of the universe, we're redefining what it means to be explorers, dreamers, and pioneers in the vast expanse of space and time. What if the universe isn't just a vast expanse of stars and galaxies, but a web of hidden connections waiting to be discovered? Wormhole theories don't just challenge our understanding of space and time, they force us to rethink the very nature of reality itself. These cosmic shortcuts aren't just tools for travel or scientific inquiry. They're windows into a universe that's far more interconnected and mysterious than we ever imagined. By exploring wormholes, we're not just pushing the boundaries of physics, we're redefining what it means to exist in a cosmos that defies our most basic assumptions. At their core, wormhole theories challenge the way we think about space and time. For centuries, we've viewed the universe as a static stage, with space as a fixed backdrop and time as a relentless one-way flow. But wormholes suggest something far more dynamic. They hint at a universe where space can fold, time can loop, and distant points can be connected in ways that seem almost magical. This isn't just a shift in perspective, it's a revolution in how we understand the fabric of reality. The implications of this revolution extend far beyond science. Wormholes force us to confront profound philosophical questions about the nature of existence. If space and time are more fluid than we thought, what does that mean for concepts like causality, identity, and free will? Could wormholes allow us to revisit the past or glimpse the future, blurring the line between what's possible and what's inevitable? These are the kinds of questions that wormhole theories provoke, inviting us to think not just about the mechanics of the cosmos, but about the deeper meaning of our place within it. But the impact of wormhole theories isn't limited to abstract philosophy. They also have the potential to transform our worldview in practical ways. For example, the idea of traversable wormholes could revolutionize how we think about exploration and discovery. Instead of seeing the universe as a vast, unbridgeable expanse, we might come to view it as a network of interconnected pathways, each one offering new opportunities for adventure and understanding. This shift in perspective could inspire a new era of curiosity and innovation, driving us to explore not just the stars, but the very limits of what's possible. Wormholes also challenge us to think differently about our relationship with the cosmos. If the universe is more interconnected than we realized, what does that mean for our sense of identity and belonging? Could wormholes help us see ourselves not as isolated beings on a tiny planet, but as part of a vast cosmic community? This idea has profound implications for how we approach challenges like climate change, resource management, and even the search for extraterrestrial life. By embracing the interconnectedness of the universe, we might find new ways to work together and build a future that's not just sustainable, but truly universal. As we reflect on the broader implications of wormhole theories, it's clear that they're more than just scientific curiosities, they're catalysts for change. They challenge us to think bigger, to imagine a reality where the boundaries of space, time, and possibility are far more fluid than we ever dreamed. And as we continue to explore these ideas, we're not just uncovering the secrets of the cosmos, we're redefining what it means to be explorers, dreamers, and pioneers in a universe that's full of wonders waiting to be discovered. So, what have we learned from our journey through the world of wormholes and faster-than-light travel? We've seen how these cosmic shortcuts could revolutionize space exploration, connect distant worlds, and even unlock the secrets of the universe itself. We've explored the challenges of stabilizing wormholes, the potential for time travel, and the tantalizing possibility of parallel universes. And we've reflected on the profound implications of these ideas, from the ethical dilemmas of interstellar travel to the philosophical questions they raise about the nature of reality. Wormholes remind us that the universe is far more mysterious and interconnected than we ever imagined. They challenge us to push the boundaries of what's possible, to dream of a future where the stars are not just a destination, but a shared journey of discovery and growth. And as we continue to explore these cosmic mysteries, we're reminded that the greatest adventure of all is the one that lies ahead, a journey into the unknown where the only limit is our imagination. As we reach the end of our journey through the mind-bending world of wormholes and faster-than-light travel, it's impossible not to feel a sense of awe at the sheer scale of what we've explored. From the theoretical foundations laid by Einstein and Rosen to the tantalizing possibilities of traversable wormholes, warp drives, and even time travel, these ideas don't just challenge our understanding of the universe, they redefine it. They remind us that the cosmos is far stranger, more interconnected, and more wondrous than we ever imagined. These 25 theories aren't just abstract concepts, they're gateways to a future where humanity could transcend the limits of our planet and explore the stars. Imagine a world where wormholes serve as cosmic highways, connecting distant galaxies in the blink of an eye. Picture a civilization powered by warp drives, traveling faster than light to colonize new worlds and uncover the secrets of alien life. Envision the profound implications of time travel where the past and future become as accessible as the present. These aren't just dreams, they're possibilities grounded in the cutting-edge science of today. But the impact of these theories goes beyond the realm of space travel. They challenge us to rethink the very fabric of reality, from the nature of spacetime to the origins of the universe itself. They push the boundaries of what we thought was possible, inspiring us to ask bigger questions and seek deeper answers. Whether it's the ER=EPR conjecture linking quantum entanglement to wormholes, or the idea of wormholes as cosmic recycling mechanisms, these theories remind us that the universe is full of mysteries waiting to be uncovered. And let's not forget the human element. Wormholes and faster-than-light travel aren't just about science, they're about us. They're about our unyielding curiosity, our drive to explore, and our desire to understand our place in the cosmos. They challenge us to think beyond the confines of our planet and imagine a future where humanity is no longer bound by the limits of space and time. They inspire us to dream of a universe where the stars are not just distant points of light, but destinations within our reach. As we reflect on these incredible ideas, it's clear that the journey is just beginning. The theories we've explored are not endpoints, they're starting points, launching pads for the next generation of discoveries. They invite us to keep asking questions, to keep pushing the boundaries of what we know, and to keep dreaming of what might be possible. So, what's next? The answer lies with you. Whether you're a seasoned space enthusiast or someone just starting to explore the wonders of the cosmos, there's always more to discover. Dive deeper into the science, share your thoughts with others, and stay curious about the mysteries of the universe. Who knows, the next great breakthrough might come from you. The universe is vast, mysterious, and full of possibilities. Wormholes and faster-than-light travel are just two of the many wonders waiting to be explored. So let's keep asking questions, keep dreaming big, and keep reaching for the stars. After all, the greatest adventure of all is the one that lies ahead. What do you think about these theories? Which one excites you the most? Share your thoughts in the comments below, and don't forget to like and subscribe for more journeys into the cosmos. Until next time, stay curious and keep